because of the sort of thoroughgoing nature of that presentation, and to allow Chris to round off, we've gone a bit over time, and so with your indulgence, I will not entertain questions now, but at the end of the presentations, if there be time. So I shall now call on Ugo Bardi. Some of you will remember him as one of your hosts at the ASPO 2006 conference in Pisa, speaking to us with respect to energy, mineral resources and energy analysis. May even include some reference to whale oil in the 19th century. Thank you.
So, hello everybody. It's a great pleasure to be here at my 6th ASPO conference. I'm only sorry that I missed the first one in Uppsala, but I've been to all 6 conferences that came afterwards, and I even organized one, and I can sympathize with those people now who are doing this work today. So, today I'm having some kind of an ambitious title, and I think I should explain to you how I got to the point of losing some kind of large amount of my time into studying this. And one thing that I discovered working with peak oil is that many people in this field are or were science fiction readers. I don't know about you. In my case, I am sure, and also about many members of ASPO Italy. A person who reads science fiction is somebody who is interested in the future. That's, I think, the point of contact of all of us who spending the time listening to this boring presentation, my boring presentation, of course. And so there is an old theme in science fiction that you may remember from those novels that you read. What happens when we run out of minerals on Earth? What do we do? And then science fiction has an answer. We just mine the moon, or we mine the asteroids and things like that. And it is an interesting idea, but when you start studying geology, then you discover that it doesn't work, because you can go to the moon, send probes to the moon and things like that, and you see this is a place on the moon, that big rock there, even as a name, it is called Tracy's Rock. I don't know why, but there is a little vehicle near it, which is probably an electric vehicle, which is kind of thing that I like. But the problem is, in this rock, there are plenty of minerals in the range of parts per million. There's a huge amount of material in that rock. But there are no mineable, you cannot extract minerals from there, because the minerals are dispersed in there. You should crush it, make it into dust, then process and then leach it, and then finally extract those tiny amounts of minerals that you can find in that rock. And that you can make a calculation of how much energy that would cost. And you see that it is impossible, at least with our technology, the technology that we can think we can have in the coming years. Bearing the idea that somebody can invent some wonderful machine, 0-point energy, fusion, cold or hot or whatever, we cannot mine the crust of the moon, nor the crust of the Earth. It doesn't change. We cannot do it, and mining the asteroids, I came all the way from Italy to telling you that is not a solution, but I'm sure that there will be more than that in this talk, I can tell you. What happens on Earth? Earth is a very special planet, which has a large number of geological processes, for instance, hydrothermal processes, which are generated by the magmatic and hydrothermal movement of the crust, which over millions of years, more or less, accumulate elements in forms that we can extract. These are what we call deposits, and those deposits that can be extracted in an economical way for a profit are called ores in English. And that's why, if there are aliens in the asteroids, they should come here to mine to extract minerals, not we go to the asteroids. And human metallurgy started with this kind of minerals, these kind of things, which are very, very special. And if you think about that, that the crustal process could accumulate copper in metallic form is very special, very difficult. But given millions of years, billions of years, maybe it can be done. And we started our technology by extracting, using native copper and others, gold nuggets and things like that, first attempts of metallurgy. But the problem is, of course, that over the years, these resources have ceased to have an economic importance. We are not mining anymore native copper. There's no more native copper in significant amounts on this planet. So what we've been doing, we're moving to different kind of things, like sulfides, like this one, for instance. This is a deposit. I don't know if this is extractable or not, but it gives some idea of what we are mining today. And as you can see, first of all, we are mining compounds which contain less copper per unit of weight. And then these minerals are much more dispersed. Typically, we mine metals in the range of 1%, a little less than 1%, a little more than 1%. This is the range in which it is economically possible to mine minerals. And even though this kind of things we call ores, it takes a lot of work, as you can see. Energy, because picking up a gold nugget is easy if you can find it. Mining copper out of these kind of things is much more complex. So the mining industry today is as an enormous, huge enterprise of things, machinery, people, mines, quarries, all kind of things, just to show you the kind of machines that we have been developed. This is something that exists in Germany, made by Krupp, I believe. This is for mining coal, and it's truly huge things. Now, I don't know, I don't think anybody ever made an energy analysis of this thing, but I'm sure it costs some money, some energy is needed to make such an object. It's a peaceful object. It doesn't look like, it looks like some kind of Japanese robot from if you look for it with Google, you can see it. There are two of them in Germany, in Garzweiler. And with these kind of machines, you do things like this. This is the Morency copper mine, and you can see the size of this object by considering that those little white specks on the left are buildings. So mining is a huge enterprise, gigantic. You're moving enormous amounts of rock. And that was the mine. That's another place with the tailings. The tailings, it's mountain ranges of tailings of copper, because it is a big change in the Earth's structure. We are already mining at least an order of magnitude more per year of the total sedimentation by natural processes on Earth. So what are we doing here? We are gradually moving from highly concentrated deposits, which took very little energy to exploit, to less concentrated deposits, which are progressively requiring more energy. And let me introduce the concept of the mineralogical barrier, which was proposed by Brian Skinner in 1976. And let me tell you that it's just a cultural element, because we don't have enough data to build this curve. For most minerals, we don't, with some exceptions. But it makes sense, I think, because there is a small peak on the right, which is the section, for instance, in the case of copper, it would be the peak of sulfides. Sulfides you can mine, and they're usually concentrated in deposits, which are reasonably exploitable. And then you have the crustal dispersion, which is an enormous amount. This is not to scale. The peak on the left is huge in comparison to the little peak on the right. So for most minerals, we have been working on that little peak on the right. With some exceptions, of course. Consider oil or coal. Oil doesn't have this big peak on the left. It's either oil or not oil. Either you have oil in a well or you don't, so you're exploiting only the concentrating deposit. Other materials don't have the peak on the right. An example is uranium. Uranium doesn't form sulfides, or more simply, those elements which are very common in the Earth's crust, like iron, silicon, aluminum, magnesium, that you mine, the concentration is around several percent everywhere. You use special ores to mine it because it is convenient, but in terms of concentration, really, there is not such a problem. And anyway, as I said, this is more for culture than everything, because we really, for most mineral commodities, we have not exploited yet the little peak on the right. If you read the data on this subject, you see that the potentially extractable resources are very huge amounts that are far from being completely exhausted. We are not running out of minerals in a geological sense, that's sure. The problem is, as I started mentioning, is energy. We are not running out of minerals. We cannot mine ourselves out of the planet, but we may be running out of energy, and that's where the problem is. Energy. If you want to move on the left in that diagram, you need progressively more energy. And in principle, approximately, it is proportional to the inverse of concentration. If you want to mine something which is 10 times less concentrated, then you need to move approximately 10 times as much rock, and then you need about 10 times more energy. So that's the problem. If you want to move along this line, you need more and more energy. And you can already see in this picture here where we stand, we are using huge amounts of energy for mining. These are just some examples that I found in the literature. I could not find, maybe some of you have data on this point, the total amount used by the mineral extractive industry on this planet, but from a rough calculation, about 10% or more of the primary energy supply is used for mining. Now you see what we have two problems. Problems never come alone. Two problems. One problem is that as we exploit resources, we need more energy to go to less concentrated resources. Second problem, probably worse, is that we may not be able to maintain the supply of energy that we have had so far. So those two problems get together, and where are we going to go now? Good question. So we, together with my co-worker, Marco Pagani, we made an analysis. We took the database of the United States Geological Survey, which lists 57 elements being extracted today from the crust of the planet, and we examined all of them to see where we stand in terms of trends. And we saw that there are several cases of curves that look very much like the oil curves with peaks. Now, before going into the data, I think we thought about that. Why do we see these curves? And we have a little model that I don't really have time to go into details, but the point that I wanted to make just quickly is that when you extract oil and a mineral, there is a difference. As we said, oil is either oil or no oil. A mineral is graded. You go gradually from some concentration to lower concentration. So it's different. But if you take into account this little model that tells you that the production is proportional to the amount of resource you have multiplied by a factor that we call capital. Capital is the aggregated amount of everything you need to extract. People, machines, energy, fuel, those big machines that I showed you at the beginning, you need all that kind of stuff. And we assume that capital is created by the profits of extraction. So if you suppose that a constant fraction of your profit is reinvested in the extraction, then this model can be solved. That gives you a very nice bell-shaped curve, which looks very much like the Hubbard one. So the point is that extracting a mineral like copper is not just a question of geology, but also on the amount of energy and the resources that you can dedicate to extraction. If this amount is more or less proportional to the profits, you will see that we have bell-shaped, Hubbard-like curves. So the first case, it was not done by us, but by Darian Anderson. They published this paper on the earth drum, and they discovered, I think was the first claim published, okay, look, phosphate rock has peaked and is going down. And that was already very interesting. So then we did all our calculation, and we found a good number of examples. I start with mercury because it's the first one that we found. Peaking maybe a little bit. It's not exactly a bell-shaped curve, but, and then people always tell me, but mercury is going down because of regulation. But if you look carefully there at the data, you see that the regulation came much later than the decline of production. And there are many examples. Zirconium, for instance. Zirconium peaks, and I know zirconium rather well because I work with zirconium ceramics in my university. That's my main work. So it's one of the examples. There are many examples. Selenium, for instance. And I could show you several cases, but not everything has peaked, of course. But you see the difference. When you have a commodity like copper, which has not peaked, doesn't show a clear peak, then extrapolation, it's more dangerous. Where do you go from here? You don't have enough data to make reliable extrapolation. So this is one of the problems. And then there are other cases like gold. Gold is interesting. I think it proves the idea that we have of the model. The model includes geology and economy. Now, of course, over this span of time, the geology of gold has not changed. But you can see here cycles which are due to essentially to economic cycles in the world economy, which affect the amount of resources that can be allocated to extraction. So you have these cycles up and down, up and down. Probably there will be more cycles depending on how the economy will go. Right now, I suppose it will go down. Anyway, what we did eventually after this analysis of 57 cases and more, because some cases made out of several kinds of minerals, we ended up with a table, which I think is the main results of our study, which I think is very interesting for one reason. And when you have a material which has peaked, so you have a reasonable estimate of how much you will extract in the future. And you can compare these results with the USGS geological estimates, reserves plus cumulative production. And you see that there is generally a reasonably good agreement of the two sets of data, which means that the geological estimates of the reserves, be careful, the reserves given by the USGS are reasonable estimates of what we will be able to extract in the future. Of course, if you go reading the tables of the USGS, they say, okay, these are the reserves and this is reasonable. They are defined as those mineral deposits which can be reasonably exploited with the present technology and economic conditions. Then there are the resources, resource base and various definitions of things that one day, in some conditions, when the price is right, you have always this sentence, will be possible to extract. Resources are usually larger than reserves. Reserves are tiny, resources are enormous. So you have this sensation that really there is no problem. We run out of reserves, so what? We go and mine the resources. But from these data, it seems that we are rather stuck with the concept of reserves, which we will not be able to exploit. What Skinner had already examined this point back in the 70s, said at some point we'll need to cross the mineralogical barrier and exploit, for instance, for copper, he made this example. When we run out of sulfides, then we have to move to oxides, but oxides are much less concentrated in terms of mineral deposits. So you need a huge jump in energy. Now, what this table is telling you that as long as we don't have this jump upwards in energy, we are not going to do the jump across the mineralogical barrier. We are stuck with limited amounts of minerals. And that I think would need very long discussion, but I just go quickly. Some of my conclusions, I won't have time to discuss the conclusions in details. But anyway, starting with an examination of what is the availability of minerals on Earth, and you see that there are common elements, rare elements, and trace elements, one of the possible subdivisions. My conclusion, which I take the responsibility of, is that we will never run out of the common metals, which is obvious, like iron, aluminum, titanium. These are abundant. We don't have any mineralogical barrier to cross. The supply is assured as long as we have energy. That's the key point. If the energy goes down, we're going to see those metals peaking as well. Then we have the rare metals, which are very important for the industrial world, for which the situation, it's both geological constraints and economic constraints. We need to increase, if we want to keep these minerals from peaking, we need to increase a little bit at least to maintain, but probably to increase the amount of energy that we'll have available, but this will be very difficult. So some of this material either have already peaked or may be peaking in the coming years, not in a very far future. The big problem is with the trace elements, which are very limited amounts of resource, very difficult to recycle, impossible in some cases. And here, to keep supply increasing, you need huge amounts in the energy availability, and that's very difficult. You already have problems with selenium, gallium, I showed it to you, indium, I didn't show it to you, but we have big problems with indium. Indium and gallium are fundamental elements in electronics. So it's not an easy problem to solve. Think of platinum. Platinum is a very rare element, and people are talking about a hydrogen-based economy with fuel cells. Fuel cells, in one of the versions, need platinum, but you don't have enough platinum. And if you were to move to extract platinum from the undifferentiated crust, it's completely impossible. You need amounts of energy that are even unthinkable. No, there's no technology that you could do. So this is a big problem. And this is conclusion about conventional mining. 1 minute, I go very quickly. So there are things which are not conventional mining, and I could spend a few hours here discussing these things, but I'm sure Mr. Chairman would not like me to stay another couple of hours. So I just tell you that about these possibilities are all very interesting, absolutely interesting, but right now are extremely difficult. And for instance, we are not going to extract anything out of seawater for the near future. No way, a no, as the Americans say. And I give you a reference, then of course I have to justify this. And just a quick word about substitution. Then what people tell me, well, then it's not a problem. We can substitute. We don't need platinum, copper, tin, etc. And on this point, I invite you to read this excellent paper, which was written in 1976, which is still cited today. And they wrote this paper titled "The Principle of Infinite Substitutability." What the problem was that people read only the title. And the title is very optimistic, so no problem. It's infinite substitutability. But if you read the text, you see that this was an excellent paper, worth reading. They saw the problem already. Energy. You can substitute anything as long as you have energy. You can substitute copper with aluminum, but aluminum takes about 4 times more energy per kilogram. And you have to correct for the different conductivity and other parameters, but it gives you some idea that if you run out of copper, you cannot change to aluminum unless you have 4 times more energy, which may not be easy in the present situation. Conclusion, you have to be creative, because I think in this paper of 1976, they already said how the world will be. You have to make a new industrial civilization with a much smaller base of elements. in it. It will not be easy, but I think it is possible if you are creative. And you see, this guy, I took the picture of him yesterday in Barcelona. And of course, he used to be a banker with Lehman Brothers. But he's being creative, as you know. So, this is not the one I wanted to show you. This is nice. Okay, that's another way you expressing the same concept. But I wanted to thank ASPO, the OIDRAM, and my university. And here are some data where you can learn a little bit more of this work we have been doing. Thank you very much.